Basically, my expanded I have 45 slots.
Really? You actually make a presentation? I swear there was a row here before. It's just like disappeared. So, like people literally like walked up, picked up the chair, and carried it to the back of the
We should have had another set of chairs here and here.
Yeah.
So we can be behind you. So that you do.
Well, so you're not seeing at the beginning of the day, people literally picked this chair.
It would actually help my line of sight if you work right there.
Let's dissolve that row.
Depends on who's talking. When Matt's talking, if he's sitting
Well, I
there.
don't want to move to the back of the room when this row is taken. Can I sit in this chair?
Yeah, do it. Yeah. That's like the roast of Chris Simon. Yeah. All right, we're gonna get started, and Max, we're doing. So Max wasn't here when we started, and he wanted to gauge interest on another discussion topic for this afternoon. Do you want to just can you give a few, I'll just say a couple minute overview?
What I wanted to talk about a little bit is there's a tool in Illumos or SmartOS or Solaris called MDB. And there's another tool called ZDB, and I'll be careful about, I'm going to turn this way. No, I'm going to come back here. Thank you. And I'll be careful not to bash ZDB because Matt's here, and I did this not too long ago and started the talk with why ZDB sucks. I'm really sorry. So the issue I have with ZDB is ZDB tends to, has anyone used it here? Yeah, so it gives you all or nothing. And so I started it when Karen was talking, and I'm trying to find a particular ZAP object because I need some information about it. So ZDB minus 8Ds, the pool name, and it started giving me the space map. You've seen this. Well, it ran for an hour and a half giving me space map information, and then I lost the connection. So I mentioned to Matt just now that actually Solaris 11, which I happened to get on not too long ago, they took the space map out of this output. It makes things much better, but the real issue is that ZDB is not really interactive, and it's very tied to the ZFS code. So in other words, it calls spot open, and if something's broken, it's not very good at telling you what's going on. In fact, it's basically terrible at it. If everything's fine, it's great because it does everything, and you can see everything that's there, and you can figure out where everything is, and that part's great. But as a debugger, I want something that's interactive. And several years ago now, I modified MDB so that I could actually run MDB on the raw disk and then look at the Uber blocks and actually walk the data. Now, this has other problems. It's very much you step by step by hand looking at everything, but you can see everything, and it helps you to understand what it is you're looking at or what the layout actually is. So what I wanted to do was show this a little bit, show what I've done. An issue with using MDB is that I haven't figured out or haven't gotten around to figuring out how to do decompression. This is the real headache. So what I want is something like :z print or print minus z or something like this, where I can say, okay, I want to decompress this block and then print it out as an offset fizzt or a dnode fizzt or a DSL dir fizzt or whatever. So that's what I had hoped to talk about a little bit, and I just did. If you want, I can go through some examples, but if you had other things planned.
So is this like a kind of work in progress?
Oh, it's very much work in progress. There's a bunch of, especially now, I'm working on a real problem. We had a pool basically get wiped out. We can't import it. If you run ZDB on it or zpool import, it complains. It complains about a couple of meta objects. But I like to look and see what's there.
Yeah, to like interactively, see what-
Exactly. I like to be able to say, oh, I want this particular object ID. I want to look at this data structure. I'd like to be able to say, here's a block pointer, : walk block pointers, and have it actually walk. If there's indirect blocks, actually walk all the indirect blocks and display them like : block pointer does. And for those who don't know anything about MDB and some of this audience,
So can we kind of gauge interest on like seeing? I guess would it be like a demo? Of this
I can show a demo
later on today. A bunch of people. Cool. So
All right.
let's. I'll put that on the schedule for later today. Hopefully we will have time. I think we're not too far behind. So there's still a chance. Adam, take it away.
Thanks.
So,
Thanks.
thanks.
Since we're so close to today, Ben, let me just change it now.
And because we know Adam's gonna run long, is that what you're saying?
Far be it from me to insinuate such things.
Um,
All right, off we go.
Great. I'm Adam Leventhal from Delphix, as you mentioned earlier. Matt introduced me as had written dtrace, which is true, but I also wrote triple parity RAID Z and hacked up gzip compression in ZFS. So I'm
I forgot that you did that.
Yeah, I did that over like a weekend. That's why it's so messed up. I'm kind of a very active ZFS dabbler, perhaps generously. So Matt had suggested this. Matt had suggested this title for the talk: data-driven development, OpenZFS. But I think more like ZFS was slow, is faster. I think captures a little more. There's going to be a choose-your-own-adventure component of this talk, so stay tuned for a second. Matt gave his version. I'm also using this as a platform grandstanding. Matt gave his version of the on the liquor box. Soapboxing, is that what your point was? This is my version of ZFS history. Matt gave his. ZFS kind of went through started its development in 2001, and kind of went through that development cycle until about 2005. That kind of initial work, and the focus there was on stability and reliability and features, and all kind of the top line selling points of it as not just vaporware in Solaris 10. And then 2006, when both ZFS shipped in part of Solaris 10 Update 2, and we started the ZFS storage appliance group, then called Fishworks, later called the Sun Storage 7000, to put it in no particular order.
And then later yet called the ZFS storage appliance.
Yes, and then eventually called the ZFS storage appliance. 2006 is both when that kicked off, and then we shipped it in 2008. That was where it underwent real significant kind of systemic testing, where we were both building an appliance around it and where customers were using ZFS much more extensively. Is this me? And then in that third stage, we actually shipped the product, and that's when we really learned where it was broken. That's where all of those features were really being used very extensively, being used in very performance-critical environments, and where we built. That's where we started to build in that real stability. And I think, as I was talking to George earlier, there felt like there have been many what felt like finish lines with ZFS, but I think we realized that they've all been starting lines, in fact. And so, the first age of OpenZFS, I think we're backdating kind of to 2010, when Oracle turned off the taps, and when all of these, a lot of the people here and a lot of people not here started up in the OpenZFS community, started building their own products on top of ZFS. So lots of different platforms and contributors and companies. And this is also where I think we started in the last couple of years doing real performance analysis on real and varied and angry and nasty customer workloads. So the content of this talk is going to be mostly data that I collected from a grouchy customer on a grouchy system. And I want to use this as a way of kind of showing some of the data that we used to fuel some of the performance innovations that we've had from Matt and George and me and others, also as a methodology and also as a way forward. The data's real. I'll try to avoid saying a customer name if I can, but I bet I will not be able to. Most of it we collected using dtrace. People have used dtrace. Good. And also Lockstat and PStat. And at some points you might say, well, what about X, Y, or Z? And the data I have is the data I have, and I'll try to get in and get more data. I wish I had more data as well. So this is the choose your own adventure part. So the two ways that this presentation could go are either snippets that I have collected snippets that I've collected in this PowerPoint document, or very sexy text files that look like this. So, show of hands, who would like the text file random walk, and people who would like the curated presentation where I've actually pulled out some of the interesting points, you might be able to see them. Nobody wants to. I made 45 slides for nothing.
Okay, fine.
A couple of people.
I want to see the curated version.
Okay.
But I've already seen this last year.
Then I tell you what, I will do some curated version, and then we'll get into the text files at some point. Actually, we'll start with the text files. And apologies to folks on the screen, because there's absolutely no way to be able to see this. And people in the back, if you start squinting, I will force you to come up here and sit next to Chris Simon. Chris George, can you read the text on the screen?
Yeah.
Can you turn off the?
I think I'm a bit
Yeah, he's got bananas. Yeah. So what if I make it smaller? Keep going until.
Come on, leave something for the camera.
Great. People on the camera, I will share my presentation someday. Good. So let me give the background. Customer is running, I explained already about Delphix. Delphix uses kind of our customized version of ZFS as part of it. We had a customer who was very unhappy with the performance they were doing on their system. So started just by looking at the performance of, and Delphix works, we're a software virtual appliance. We connect up to any storage. In this case, it was a EMC SAN, and connect up to their Oracle database. So in this case, I went onto the customer system and measured latency at the I/O layer. I'm going to explain this once, and I'm not going to explain it again. So these are dtrace histograms. All the times you're going to see are in microseconds. Usually there's something that says microseconds there to try to label the axes. So this is what we're seeing from their back-end system. This is reads on the top. Why do we see a bimodal distribution? Shout it out. Caching. Matt, ruining it. And then on the right side, we're seeing kind of like a pretty lovely distribution around 2 to 4 milliseconds. So the back-end storage seems really happy. Now, then we look at NFS. Cached reads look great. Uncached reads kind of had that same bimodal distribution that we saw from before. But when you get to the right, we're starting to see really awful stuff. So this is on the top async writes, and these are sync writes. We see this kind of trimodal distribution. Some writes are super fast, like microseconds. Then we have a little hump around 8 milliseconds, and then another hump around 2 seconds. 2 seconds of latency per operation, which is pretty bad. So looking at that, we understood why the customer was cranky. I'm going to start there. I'm going to go over to the curated slides just because, but I promise I will get to the ugly mess at some point. So this is the picture you just saw. Sync writes were bad. I/O writes seemed fine. This is another thing I pulled from our graph. So this is an example where we didn't, before you saw kind of most of the writes were pretty fast. Here we're seeing many of the writes are 2 and 4 seconds and longer. And this is a system in serious pain. So the first problem I'm going to talk about is the write throttle. So we looked at, we used this dtrace script to see how long spasync is taking. So when you enter spasync, we counted the amount of time and we keyed it by the number of space map loads that happened along the way. And we saw spasync was taking, this is where to focus your attention. Spasync was taking 1 to 2 and more seconds. Now, I'll get into an explanation of what's going on. Then we looked at where is spasync giving up the CPU. So the thought here was spasync is taking an awfully long time to run. Spasync is the thing that writes out all of your data to disk. It's taking a long time to run, so we wanted to understand why it was giving up the CPU. So every time we went off the CPU, we were taking a timestamp. Every time we went back onto the CPU, we were taking another timestamp to see where we were giving it up most frequently. And we saw that where we're giving it up most is on this DSL pool sync on ZIO wait. Actually, that was probably the wrong one to pull out. Sorry, but I'll press on. I'll get to the more salient data on the text file. So ZFS write throttle. Has anyone looked into the ZFS write throttle? Yes, a couple of people. Maybe before Matt pushed the better ZFS write throttle. Had anyone looked into it? A couple of people. Great, same people. The old ZFS write throttle worked roughly like this, and Matt and George just keep me honest here. We want to keep transactions to a reasonable size and limit the amount of outstanding data. And it did this by targeting a fixed amount of time. So on some systems it was 1 second, and others it was 5 seconds. And it basically worked like this. Let me accumulate as much data as I can write out in 1 second or write out in 5 seconds. And I'm going to figure that out based on some sort of notion of history that was not particularly well formed. Once I've gotten that much data, stop. Just wait. That transaction group is done. We need to not make it any bigger and sync it out. If there's someone already syncing, then everybody needs to just stop. Now here's the really quirky thing. When we get to 7/8 of that limit, it inserts a 10 millisecond delay. I just have no idea if you look on the web, you can find some rationalizations for why this is a good idea. It's basically like when we're getting close to the wall, then start to slow down the incoming rate or something. But you can see it in the data. You can see that we have a bunch of stuff that is lickety split, and then we have this pile of stuff that's about 10 milliseconds because we've inserted some random delay, and this pile of stuff down here which takes multiple seconds. And the stuff that takes multiple seconds is because we've reached our limit and we're not allowed to go above it, and the previous transaction group is taking several seconds to go through. So we wrote this dtrace script, and you can kind of parse it on your own, but to look at what the inferred limit was. So ZFS was, the write throttle was trying to figure out how much data can I push through the system in the amount of time that I have to push it through the system. And it was doing this based on some kind of notion of hysteresis. Measuring this, it would vary widely. So on the left you have seconds, just how many seconds since I started running the script. On the right, you have the number of hyperinflated megabytes that it thought it could write through. On this sample, it varies anywhere from 470 to 670 megabytes a second. On the system, just anecdotally, I saw it range anywhere from 100 to 800 megabytes. So what that means is our notion of how big a transaction group is deeply flawed. It's ranging all over the place. So it means we'll try to make a big transaction group and then swing the other way and make a small one. And sometimes we'll be blocking, and sometimes we'll be snapping off transaction groups all over the place. Also, reads impacted this, so it was a mess. Another problem. I'll get to a solution. So we're looking at IOQ times. Have people read Brendan's lovely blog post about the use method? Robert was already raising his hand before I even specified what blog post it was. So, yep, I've read it. Great. So the use method looks for, in particular, looking for places where we're queuing or where things are saturated. So in this case, we were looking at IOQ times, and we saw that there was a bunch of work in the IOQ for synchronous writes that ZFS was queuing and not pushing to the backend storage. If we look at async writes, it's an even sadder picture where we see things that are, our peak for things being in the queue is around 250, 500 milliseconds.
But, I mean, this seems like consistent with the fact that it takes 1 second to sync out each TXT, because like async writes, we create all these, as soon as we start syncing, we go and say, okay, great, create a bajillion async writes and put them into the queue.
Yeah, fair enough. Okay. So maybe I'm making a mountain over a molehill on this one.
Well, on this one, I think it's
Can we look at this one then?
Yeah, look at this one.
Good, okay. Because we still have things hanging on the queue for an amount of time that is similar to the amount of time it takes to service the I/O. So then we started looking at the queue depth, ZFS VDEV max pending. Has anyone kind of turned this knob? Okay, great. Lots of people have turned this knob. This is a great knob to turn.
Now you're gonna have to turn a different knob.
You got a different knob for you now, right?
Now you have like 4 knobs.
This is this particular customer system with a queue depth of 10 and kind of a similar workload. There are fluctuations in the workload. So this is queue depth of 20. You can see it kind of shifts down a little bit. Queue depth of 30.
This is all on production, right?
This is all on their production system under load. Queue depth of 64, and we also get average latency down here. So the average latency is 44 milliseconds, which is already getting to be kind of a long time for a storage array to respond. And then queue depth of 128, 88 milliseconds now. So we're kind of leaning on the system more. The latency is going way up, but the throughput is only increasing a little bit. So some I/O problems. The choice of the I/O queue depth was obviously very important. We've all, as evidenced by all the hands going up. I don't know where the default of 10 came from. Maybe that makes sense for disks. I suspect it does not make sense for disks. There's some people in the audience who deal more with physical spindles more than I do. What do you use as your queue depth?
We use 10 for SAS drives and 4 for SATA drives usually.
Okay.
We try to stay away from SATA drives in general.
Okay.
And for solid state, you can go up to 32, 64.
Okay. Interesting.
It used to be 30 when it was first integrated.
I see. So and then you take out your 100-sided die and roll it. Right. Plus the dexterity on your drive. So obviously this is a balance between the settings. It forms a balance between latency and throughput. We also have a single shared queue for reads and writes, and maybe this makes sense for physical spindles. I don't know that we have data to suggest it does or it doesn't. It probably doesn't for the types of systems that we interact with, which are usually large NAS or SAN systems that have dedicated hardware for writes and other hardware for reads. We're not necessarily contending on the same resource.
Probably the types of systems that some of your companies sell.
That's right. So one of the big lessons that we learned here as a company that sells a product that sits between a very trusted storage box and a very trusted database is that if we start queuing stuff inside of our product, inside of ZFS, because it feels like the back end can't keep up, it doesn't really, the problem doesn't light up in the way that we'd ideally like to. For example, if we say to a customer, your back-end storage looks slow, and we show them the picture, we show them this picture, like, what do you mean my back-end storage looks slow? My back-end storage looks awesome. But if we show them this picture, they say, yes, my back-end storage does look slow. So there's an important point there to pick, depending on where you decide to queue, it can show the problem in different areas, which can help or hurt depending on what part of the stack you care most about. So for this, Matt and I scratched our heads until they were wrong to think of this new this new this new IO scheduler. We kind of talked about it as a new right throttle, but Matt kind of insisted on referring to it as a new IO scheduler, which I think is a much better way of thinking about it. The basic way it works is we choose to limit the amount of dirty data on the system, the amount of modified data that we're allowed to accumulate. Now, as more dirty data kind of builds up, we schedule more concurrent IOs. So if you have kind of a light stream of data accumulated on the system, then we will optimize for latency. Now, as more and more data builds up, then we're going to start optimizing more for throughput effectively. We also have limits on the different types of IO: synchronous reads, async reads, synchronous writes, async writes. If we can't keep up, so if we've got the pedal to the metal and we're still accumulating more data, dirty data in the system, then we'll start to insert a delay on the inbound traffic. All right. Now, a question came up when we were having a snack earlier about how we roll out some of these performance enhancements. It's a great question because we can't, in our labs, in Delphix's labs, in your labs, we can't exhaustively enumerate all the different types of performance scenarios that all of our customers are going to experience. So what we tend to do is choose defaults that are safe-ish, that feel as close to what we were doing before as possible. With the knowledge that with all these different customer workloads, what we need to do is try to match the performance and the behavior that they had seen previously, but build the right knobs for us to be able to adjust our algorithms according to their workloads. So in this case, we can expand the size of that dirty data window to allow more or less to accumulate, and then change the number of concurrent IOs, the IO queue depth for all of those different queues, as well as a master queue, or a global limit, I should say. And then change kind of factors that have to do with how that delay ramps up. Any questions or comments about the IO scheduler or other data you might want to see?
If you've looked at porting this code to your platform, you may have read some enormous, very informative comments in the code that explain how all this stuff works. Adam wrote all those comments.
So Matt gets to take credit for them. But
No, I'm giving you the credit right here.
But it also kind of a put up or shut up moment. It was one of those code reviews where I'm like, a comment here would be great. Do you want me to write it? He's like, yeah, write it.
For those of us that that was immensely valuable.
Okay.
Yes, thank you.
That behavior should be encouraged.
There's also like graph viz, like plots in there and stuff. Yeah, was there a comment on that?
Yeah, no. So the first thing, the defaults that whatever was there that I ran into was.
What are the specific defaults? I don't remember.
What are the defaults with the new 40456, right? One of the first things I ran into was a lot of block contention. So the IOs just stalled. We just ran a basic IOs on throughput workload, and unless we kind of increased all this different, we have read write queue depths to long, a lot more, and 30 max to like almost -1. We couldn't get the IOs to compare also. I don't know.
That's useful to know. So either fix it or file a bug or share the data.
It'd be good to get some data on that.
Yeah, I have some MDB factors.
Yeah.
Yeah, I just got done benchmarking the Linux port of that past the new IO scheduler to put up some graphs on the biggest up-pull request.
How'd we do? Good or bad?
Saw some interesting behavior that I don't think that we need to understand better. In particular, at high thread counts on large pools, like pools with many physical VDEVs, about like, for example, RAID Z2.
What do you mean by thread counts?
So I was running FIO, and I was just ramping up the number of threads that FIO uses to do IO. So I think they call that parameter the number of jobs.
Okay.
So like when I got up to 6,428 threads, the performance with the patch kind of nosedived. And this is with the default. So I haven't looked at, need to pick different queue depths or...
So there are a couple of things here. So one is, It is not our expectation that the new IO scheduler will be strictly better in all cases yet. The goal is to have something that is you can reason about in some rational way. The old IO throttle was kind of like, let me roll the dice and pick how big this TXG is going to be, and then I will stop you in your tracks if you're too big.
Right.
And the knobs you could turn were so kind of oblique and removed from any real understanding. So now at least our goal was to put in knobs that made sense. Now it might be the case that your workload is slower with it, or that you run into lock contention. If we did nothing, we would never have that data. And so that's one of the reasons we moved forward there. And again, it's like we can reason about how big that window should be. And we can look at the amount of memory on the system and kind of the throughput of backend storage and figure out whether it needs to be 500 megs or 4 gigs or whatever.
This isn't hyperinflated megabytes.
It's a quantity that you can kind of ballpark and bullshit about and also measure. Then there's stuff around the IOQ depth. It's another thing that you can measure. It's another thing that you can interrogate the backend storage about. It's another thing you can experiment and do based on data. And then the delay time similarly. So these are all primitives that make a lot more sense. Now, if we whiffed in terms of like introducing massive amounts of lock contention, we'll go fix it. And
these are definitely things that we measured. So it's like I measured lock contention with like 64 threads, all like issuing concurrent writes and stuff, and it looked good. So
that's we didn't just throw
miss something there.
Yeah.
We care about these issues. Is the point that I'm making?
Well, and we also did our own testing. We just it is. I'll never claim that we did kind of representative testing or systemic, or statistically relevant testing or exhaustive testing in any respect. We tested a bunch of stuff that was relevant for our customers and our use cases and the stuff that we could think of, but we could test forever and still not get enough testing.
Yeah, and I didn't raise the point to say that it's screwed up or anything. It's just this points to some areas that we want to look at.
Absolutely, and it's great feedback in that. So, on the subject of lock contention, I want to pull up some examples. So, on this system, we started looking at lock stack. Can people read this in the back? Great. So, just keep in mind this particular lock. We see a task queue where we're blocked for a damn long time. And this is also spinning. So that means and this is in nanoseconds. So down here we're spinning for like, wow.
6 seconds?
No.
67 seconds.
67 milliseconds. Which is like, it's a long time for a CPU to spin.
To be a spinner.
Yes. Right. That's a long time. But, so we're spending a tremendous amount of time spinning. So this is obviously some awful contention. Same lock, different place, just as bad spinning. Same lock, different place, just as bad spinning. This is data we collected over a year ago. So this predates that IO scheduler. And so. Let me kind of tell the punch. No, let's just keep going down the list. So then there's some ARC MRU lock where, wow, that's even worse. I didn't even notice.
Oh, I fixed this one too.
Okay.
Pretty sure.
Pretty sure. Good.
Well, I fixed a bug that would manifest itself that way.
Got it. More ARC locks. Now adaptive mutex block. This is that same thread, same lock. Pardon me. Similar MRU lock, I believe. So we spent a lot of time looking at lock stack on this system in particular because the lock contention was so ugly. Let me see if I can get down to where we actually do something about it. These text files are needed to be curated a little bit because it was kind of like a random, what do I want to do? Random stream of consciousness in terms of like the stuff we looked at. All right, back to the PowerPoint. So that's what you saw from Lockstat. And we found it to be this lock. So it's the ZIO write issue lock. So has anyone been kind of deep in the bowels of ZIO? lots of task queues. There's like this static block of code where it says like this task queue should have 6 threads and this should have as many threads as there are CPUs, and again, magic numbers that fell from the gods or not. And so in this case, we saw a massive lock contention on this particular task queue. And so we broke up that lock in a fairly gross way by just making a bunch of task queues. So rather than one task queue that had like 24 threads, we had 6 task queues that had 4 threads, and then doled out the work based on what get HR time said. So fairly inelegant, but it kind of distributed that work. We had a similar problem on the read side that we hit recently on a different kind of benchmark. So there's other kind of lock contention issues still in the world, and there's work to be done there. And definitely, I would really welcome any kind of lock stat output or lock contention input. Yeah.
We have lock code previously. I assume you guys have that.
Yeah, that's what we've been looking at.
Oh, okay, sorry.
Sorry, this stuff was from Lockstat, which is kind of a wrapper on dtrace, but it is looking specifically at lock contention events. But yeah, if you have other or better analysis tools for looking at lock contention or other workloads that exhibit, heavy lock contention, there's a bunch of data that we've collected here, and we can. Those task queues kind of dominated it, but I think.
Do you want to maybe just tell people like what information this is gathering? Just like
Lockstat in general. Yeah.
Sentences.
So yeah, Lockstat, pardon me, is looking for, in particular, here we're looking for contended mutexes. So we're looking for mutexes where I went to acquire it, but I wasn't able to because someone else had it. In Illumos, and forgive me, I don't know about the other operating systems, but in Illumos we have adaptive locks. Adaptive locks will say if the thread who owns this lock is on CPU, then I'm going to sit here and spin under the understanding that we've optimized the system for the uncontended case. So if someone is on CPU and has the lock, they're probably going to drop it in a moment, so I shouldn't bother going to sleep and being woken up. So it shows both those types of events as spin events. It also shows blocking events where where a thread has actually put itself to sleep in order to wait for that mutex to be handed over. Lock contention obviously really impedes performance, or can potentially really impede performance, especially when you're locked for a very long time or you're spinning for a very long time.
So this is showing us like this particular lock with that address is this blocking or spinning?
I think it's spinning.
Was spinning when called from this stack trace on the right, and it spun. We detected 97,000 spin times that it came in here and spun, and then this is showing how long it was spinning each time. So most of the time it was spinning for 16 microseconds, but then a few times it spun for whatever that is, an entire second. Is that an entire
I think it's
second?
100%, 10th of a second.
A tenth of a second.
So if you want, we can kind of go down through here. There's lots of lock contention events through here. We looked through some of the good ones. Arc state change. We've seen other lock contention there. What was the other lock that you broke up with the aggregation of kind of like accounting information?
I didn't really do that.
Okay.
It didn't. There's more work to be done. So
Okay. So there are other locks that need to be broken up that we have data for. And if you like breaking up locks, we'll try to make that available on the OpenZFS website in terms of like some data you can use to see that. Okay. Back to the.
I think the main lock breakup that we did as a result of this was the stuff you mentioned for the task queues, and then not actually lock breakup, but making sure that we drop the arc. There's some giant arc lock that is held for a long time when we're evicting stuff from the arc, and it was just like grab the lock, evict however many gigabytes I might be trying to evict right now, and then drop it. So I just made it like drop the lock and call yield essentially, like every whatever it was, 1,000 times through the loop.
So there's other lock condition, as I mentioned. I'd also say that this task queue stuff kind of has solved proximate problems, but I think there's probably a better way. And I'd be very interested if someone wanted to tomorrow at the hackathon maybe work on something like statistics around task queues to evaluate how often are my threads busy, and how often is my lock contended, and maybe even this idea of a dynamic task queue that both can scale in terms of the number of threads and scale in terms of the number of locks or number of queues. All right, the next one falls in the category of space map shenanigans. So we looked at this picture of SPA sync. Again, SPA sync is called when we're writing out all of this data to disk, we're flushing all this data to disk. So previously, kind of either once every 5 seconds or once every 1 second. Under the new IO scheduler, it's when we've accumulated enough data that we've decided to break off a new transaction group. And so here we looked at all of the functions that it calls and the amount of time, the percentage-wise that we spend in it. And I hope you guys can see at the bottom. I think I have this. So DSL pool sync is where we expect to see most of our time being spent.
Can you guys see the bottom?
DSL pool sync is where we're expecting. It means we're actually writing data out to disk. But we were kind of surprised to see VDEV sync done taking up as much time, at least I think we were surprised, I was surprised, to see it taking as much time as it did. And in this case, it was about 16%, but we saw it go up to about 20%. Ideally, we want to spend all of our time in DSL pool sync, and none of, because that's when we're actually doing the work of writing data out to disk. So then we chased this down. We wrote a bunch of, this is fairly ugly. What I did was take MDB, basically MDB disk, pipe to grep, through a Perl script to write a bunch of dtrace scripts. So this was to say, tell me everybody who, I just want to trace everybody who this calls.
This is because you want to turn on all FBT probes.
That's right. I didn't want to turn on all FBT probes because I wanted to limit the performance impact on the system, and FBT : can impact the system performance. Just try to figure that out. So what is VDEV sync done doing? Well, mostly it's calling MetaSlab sync done. And what about MetaSlab sync done? Well, it's spending most of its time on space map unload. And then we started looking at all of these different space map functions and where we were spending our time during a particular SPA sync. And man, we were calling some of these just a ton of times, and some of these were taking a really long time. So this started. So George started catching wind of this and started getting interested in what the heck was going on here. We also used the CPU performance counters. Has anyone used the dtrace CPC provider? Good. A couple of people.
Once.
Yeah. I mean, it's like I worked with John Haslam on this ages and ages ago and never really used it in Anchor. But we started looking at the CPU performance provider in particular, looking at data misses on the TLB, and saw some of these space map operations and MetaSlab seg size compare coming up a lot, a lot. Now, also LZJB and something from the network driver, but this was a little more surprising. So there are a bunch of things going on here. Delphix is a bit of it pushes ZFS in a couple of ways. One, we are mostly dealing with small record sizes, 8K record sizes typically. A lot of the work that we had done previously focused on large record sizes. And when we have small record sizes, it means that these MetaSlabs can get very, very Swiss cheesed, as we like to say. And so most of the space maps on each MetaSlab had upwards of 30,000 segments to keep track of what was free and what was allocated. So I think, George, did that feel large?
I think at the time it probably felt large. As we dug into it, it feels small.
Right. So I think at the time we had kind of imagined these space maps being a little more nimble in terms of data structures. and then found that the reality of our workloads, which are small blocks, lots and lots of rewrites, at random places throughout the file, very little sequential access, meant we were Swiss cheesing these files tremendously. We also found that we were trying to build the perfect space map, and this is an observation that Matt had. We spent a lot of time kind of taking all the data we had and really making sure that the thing that we wrote out to disk represented the absolute best canonical form of the space map when we were writing. That is to say, is it just the allocations?
It would just be allocations.
So it was just alloc. And Matt had an observation, well, it wouldn't be so bad if we had mostly Alex and a couple of frees at the end, or a couple of, if we had not the optimal representation, but a representation that was a good balance of space consumed on disk, but also the amount of effort it took to create this space map. So we determined that close enough would work for a lot of these cases. Then we were doing just a bunch of work that felt very much like digging a big pile of, digging a big ditch and then filling it back in. So in particular, we took this 30,000 element space map, walked all of its component segments, and then put them on a different data structure. So it was just sitting there, kind of like moving things from one pile into another pile. And George and Matt helped the observation that we could just do some kind of pointer swapping and get out of doing all that moving around. And so George did that work. Maybe you're going to talk about that in the next slide.
I'm actually not going to talk about that.
Okay.
I'm going to talk about more recent stuff.
Okay, good. But we saw a nice performance win where we had been spending, 10, 15% of the time in multiple seconds, like 3 seconds out of 20. It was 3 CPU seconds out of 24. There were 24 CPUs on the system, just moving shit around.
And this is both like, we're burning a lot of CPU on it, but like, CPUs are fast and you've got a lot of them, but not only that, but this is like time that we're like leaving the disks idle. It's like, if you're trying to write as fast as possible, that is 100% performance left on the table. So it's like, we decrease that to 0.5%, and it's like, you get 20%, you can write 20% faster.
Yeah. And when you tie this back to like the right throttle stuff that Adam was talking about, where you can get situations where all your clients are blocked until a transaction group commits.
They're also waiting for
They're
this.
also waiting for this. So it's like everything was kind of like this cascading effect. We just get snowball.
Awfulness upon awfulness.
That's great.
So why do you suspect the memory was taming in this case?
Why?
Why? From space map.
Like, why did we start looking at that? I think, on this system, there was like, I think part of it was we were spending a lot of CPU time, and a lot of CPU time that was disproportionate to the to like what it was doing. You disassembled the function, and it's like a couple of loads. You're like, how could we possibly be spending 3 seconds of CPU time in there? And we have our performance expert at Delphix actually did a lot of work at AMD previously. And so we kind of talked to, he kind of walked us through, I can't replicate it, but it's like, what if you hit in this cache? What if you hit in that cache? What if you go to, a remote CPU, a remote socket? And what if, all these different layers of missing? And it was kind of like, only if we missed everywhere were we kind of, you have to miss in a bunch of TLBs is what we realized in order to get the type of slowness that we were seeing. So that kind of put us onto it. But I think it's a good general technique. Just throw CPC at it to see if anything lights up. Just like it's a different type of profile. All right. Any other, maybe Delphix folks? Any other pieces that you remember from the analysis that I could pull up in the text files? This is a long shot here. I'll just kind of, as we're walking through doing that in particular, we looked at various sync passes and what was taking a long time. We wrote a lot of kind of ad hoc scripts here. SPA sync goes through a bunch of iterative passes where first we wrote out most of the data, and then we write out the metadata, and kind of it eventually stabilizes. And we're also looking at how many passes it would take to complete. Thus led to some work that George did as well to to make it converge a little faster.
Yeah, we were finding that it was, so some time ago, and I think it was probably when you were working on a BP rewrite or something, we had anticipated that we might need to do our deferred freeing operations in later sync pass, or allow freeze to actually happen in both like sync pass 1 and sync pass 2. So we were deferring when you actually avoid freeing till later. That was resulting in like sync to convergence taking much longer. Like we would end up with passes that were like 9 to 12 passes. And so we started playing around with that value and saying, okay, defer freeing after you get past sync pass 1. So only process freeze in the very first sync pass, and then after that, wait till the next transaction group.
And if I understand correctly, you're also expecting most of the data to be pushed out in the first pass.
Yeah.
So it was kind of alarming and surprising to see those taking a long time.
Most of the data is pushed on in the first pass.
Yeah, it's just
29 megs and then 0 in the subsequent ones.
Right, it's just taking a lot longer. I think actually there's some note down here. Yeah, I think we actually I think that's wrong. But this is why it's uncurated. But we also, the things to highlight here are, it was, sync pass 1 took in this case, the minority of the time. And also took 12 passes to finally converge. And all of this was also throwing off the calculation of how much data we can push out in a given transaction group. So it was this feedback loop of brokenness again. All right, and there's much more data, and feel free to grab me and we can go through these. Oh, this is like one of these awful dtrace scripts in terms of like all the things that something calls. And there are lots of ones like this in here. All right, so my last slide, wrapping up. This is kind of calling a shot on the next stage of the OpenZFS. Obviously, we're very excited about all of the OpenZFS products that are coming through, the variety of use cases and demanding uses that ZFS and OpenZFS are now being put through. But I think most exciting is some of these data-driven discoveries. Sitting with Matt and George a few months ago after we kind of collected a bunch of this data, we realized and just talking through all these solutions, we realized we were really at the beginning again of this new era. There's a lot, and George's going to walk through a lot of the work that he has ongoing and that we're looking at in the future. But all the stuff around, kind of all the stuff we can do with the I/O scheduler. Now that we have this notion of idleness on the system more concretely expressed, we can do things like schedule scrubs more intelligently, or do something kind of like the IRAW that you see on some hard drives in terms of reading after write to verify that the data is correct. And there's even a possibility potentially of learning more about how the physical drives operate, and or the LUNs, the virtualized LUNs operate, to tune some of our algorithms so that we're more intelligently, the software is more intelligently choosing between throughput and latency, and we're not just foisting that all onto the user. So that's what I got. Any questions or comments? Or data you'd like to see? I might even have.
I got kind of an open-ended question. Is there any way that we can engage, or like things like this, we can engage the broader community with? Because I know on our systems, like the past year, 6 months or so, we've come to the same conclusion that like the right throttle is broken. And then, a week later, Matt comes out with his patch. We're like, holy shit, everyone else sees the same thing. Yeah. But yet there's no, like, if I see a problem, I go to Brian, who's right next door to my office. Like, do you see this? We talk about it and we bullshit, we figure out what the problem is. But there's no discussion outside of individual companies. And I'm sure we see a lot of the same problems. And my guess is you guys work on these problems for a long time, and then you push a patch and it's like, we've been seeing it for a year, here's a solution. It's like, oh, well, we've been seeing it too when we did all the same work. We've been working on the same histograms. Maybe we should have been communicating and instead of duplicating all the effort.
Yeah, I think that's one of the places where I'm hoping this kind of new OpenZFS community can fill in the gaps a bit.
Sure.
Obviously, when you're seeing things on some of this can be a little sensitive.
Yeah,
Right? If
definitely.
we have sad customers, we don't necessarily want to broadcast that. All of our customers are happy now. Internet. But you're right. If we can, maybe there are kind of other ways we can communicate, even in the open forums, to talk about kind of in the abstract the types of problems that we see. You know, the types of performance problems we see, like the bottlenecks we see.
Yeah.
You know, lock. Has anyone else seen lock contention on the ZIO right issue lock? You know, that kind of stuff. You know, I think the OpenZFS mailing list would be a great place to do that.
I think the mailing list is a good place to start sending that out. I've also been hanging out on the IRC channel,
Yeah.
so that's a good place to do more interactive things where it's like, oh, I saw this. Oh, can you give me this? Can you also get this information? It looks like it might be this problem. Okay, you know, go run it and kind of work more interactively with people.
Yeah. And in particular on feedback for the new IO scheduler, you know, we'd love to get the data to show why it's good or why it's bad. And I'm hoping also to share a bunch of the scripts that I've presented here. I will definitely share the slides. If there are scripts or data collection methodologies that, you know, most of it is pretty kind of meat and potatoes detracing, but if there's stuff that would be useful, I'd be very happy to share it. So just contact me if I haven't shared it more proactively. Cool. Great. Thank you.
Thanks, Adam.